Hi everybody, welcome to another video on Calculus 1, section 5.5, Substitution Rule. So this is as important to integral as chain rule to derivative. With this rule, we can integrate a lot of integral, right? So by nature of it, I would say this section is the second most important of the whole Calculus 1 class after the chain rule. Right. Now, so what we have here is actually the proof is from the chain rule. We have u equal to g of x, and now the function is of f of g of x, which is here of course is u, and then this will be equivalent to du, and then we just integrate both sides. So the proof is very simple. If we have u is equal to g of x, when we take derivative du over dx, that is the derivative, we can just say g prime of x and multiply dx on both sides. That's what we have. So u is inside, and that is du, du, and du is equal to g prime of x dx. So that's why we have just f of u, and this is du. So simple enough. Right. So the integral, if it is in terms of x, we will write that in terms of an integral in terms of u. Evaluate this, and after that, we rewrite the answer in terms of x. So the step is, of course, the most important is knowing what is the substitution, what do we let u equal to, and then after that we solve for this. And then we integrate in terms of u, and then must write the result in terms of x, because the original problem doesn't have u in it. Right. So from the problem, we have to write in, of course, write the left hand side, and then we can write that equal to everything in terms of u, and then we integrate. So let's look at the first example. You'll get the idea. Right. So when we look at this, we have to know what is the substitution. By the way, this is not the way I do it, but I just want to do it like what we have here and what the book has. So usually just like integral, it's just like derivative in the chain rule. What do we let equal to u? What do we put inside the box? Or in this case, what we let inside the parentheses, usually that will be u. So in this case, let's say let u be equal to x plus 1, right? And after that, we can take derivative u prime or du over dx. Either way, the notation is the same. Du over dx, the notation means the same thing. Du over dx, derivative is going to be u 2, right? Derivative 2x plus 1 is 2, and then multiply the dx over right. So we have du equal to that. Now if we rewrite this problem, I'm going to move the 2 next to the dx. If I rewrite like this, 2 dx here, of course, it's going to be du, right? And 2x plus 1 here is u. So this problem will become u cubed du. The integral of that is u increase the power by 1 divided by the same thing. Let's see. And finally, of course, to have 4 at the bottom, we can say 1/4 times u to the 4th plus c. And finally, u is equal to 2x plus 1, and that's what we use. That's what we have. So, simple enough. However, I'm not going to do it like this. Even better. Instead of write du equal to something, I highly recommend that instead of doing this, write that as dx equal to du over u prime of x. And then substitute into our problem. It will be even better. So, the most important in the substitution is 2 steps. Identify u and then solve for dx. So this is the first step. This will be the second. Yeah. So I'm going to use like that, not like this. This is how the book does it, but I'm not going to write like that. Just take one more step and solve for dx instead. You will see that it will make a lot easier and less room for error. And that is important, right? Easier to replicate and less room for error. Right. So when we look at the problem, of course, you have to identify what is u, and then we solve for dx. Pretty much it. So here, I'll let u equal to 5x cubed minus 2. And then we can check derivative, right? Derivative is going to be 5 times 3x squared. Or 15x squared. I just say 15x squared directly. Move the dx over. And then I will solve for dx. To get dx by itself, I'm going to divide the 15x squared to the other side. And that will give us dx. So 2 steps. Identify what is u, usually inside the parentheses. And then solve for dx, u and dx. That's what we need. Right. Then we can go back to the problem. Original problem is that. Just rewrite 2x squared still there. And then sign. Did let u equal to 5x cubed minus 2. So I have sign of u. dx we solve for is 15x squared. Du over 15x squared. So we have du times 15x squared. That is just time dx. So we times du over 15x squared. Right? Now, what we have here is the x squared and the x squared cancel out, right? X squared and the cancel x squared. We have 2 and 15 2 on the top, 15 at the bottom. Those are constant. We can take it outside the integral. The 2 bring on the top, the 15 constant at the bottom. We stay at the bottom. So when we write this, we have the fraction. The 2 is on the top. We can take the constant outside. The 2 on the top, the 15 at the bottom. And when we write all of that, almost everything's left with this sine of u du. And then sine of u, the integral of that is negative cosine. Because the derivative of cosine is negative sine, and we have to do one more negative. Plus c. And multiply that, give us negative 2 over 15 cosine of u plus c. And then finally u is 5x cubed minus 2. So the answer is negative 2 over 15 cosine of 5x cubed minus 2 plus c. So this is a standard substitution problem. What we need is write down what is u and then solve for dx. Once we know u and dx, substitute into the problem. If everything works out perfectly, all the x's cancel out. We can move the constant outside, and then we just have an integral in terms of u, where we can integrate, and then after that we can substitute back in terms of x, and that's pretty much it. Now we have more example here. Evaluate the following integral. So now if we see something like this, it will be more useful if we just move the dx on the back. So I will write this as 1 over 3x minus 2 cubed dx. Right. So in this case, we will use u. Let u be 3x minus 2, usually inside the parentheses. And if it works out, they should, when we have the integral, everything will be in terms of u. Right. So if that is the case, we'll take the derivative and we'll solve for dx. Derivative is 3. Multiply dx both sides, and then divide by 3. So du over 3 is equal to dx. Then we can continue our problem. We have 1. 3x minus 2 is u. That's what we left equal to, right? So we have u cubed. Dx is du over 3. That is dx. Right, that's what we have. Now from here, we have 3, the variable, the constant. Can bring it outside the integral. It is at the bottom, so it will stay at the bottom. And there's nothing on the top, so we just put 1 to hold the place. So we have 1 over u cubed du. So they give us 1/3. U cubed, if we move from the bottom to the top, u cubed becomes u to the negative 3. because we're going to use the power rule. And then we have 1/3. Integral of that is u to the negative 3 plus 1. Negative 3 plus 1 is negative 2. Divide by the same thing. Plus c. Of course, we can flip the negative 2 becomes negative 1/2 times 1/6, or just multiply across. Either way, we should have negative 1/6. Yeah, just multiply the negative 2 to that side, and then u to negative 2 plus c. And then finally, we can replace u with 3x minus 2. Yeah, so just use the power rule here. So if we want to, that negative power move to the bottom. Become positive, then plus c. So we certainly can do that. Let's just put the 1 in the middle, right? So yeah, oh, simple enough. When you get used to it, it kind of like the routine u and dx. Substitute back in, it works out perfectly. There should be no more x. Integrate in terms of u, and then substitute back in terms of x. So that's pretty much it. Right. Right. The next one, what do we let equal to when we don't have the parentheses? Well, in here we see the cube. That is the same thing as cosine and cube, right? So we do the cosine first. We write a cube like that, and then sine of x dx. Right? The cube is like that. Then of course when we look at this, you know what we have to substitute, right? Okay. Inside the parentheses, cosine of x, right? Now, not only that, usually whatever we let equal to u, where we take the derivative of it, it have to resembling what's left of the problem. Now, if we let u equal to cosine, the derivative of cosine is sine. We should cancel with this, because the point here is after the substitution, there should be no more x. So whatever we let equal to u, the derivative of that must somehow resembling what's left of the problem. Right. So that's the key of the substitution as well. So in here, we let u equal to cosine of x. Now we just take the derivative. Derivative of cosine is negative sine. We can move to dx. And then solve for dx and divide by negative sine. So write down u and then solve for dx. Then we can substitute back into our problem. Cosine is going to be u and then cube. The sin x stay there. The dx is du over negative sine x. Right, that's what dx is. So solve for u, I let u equal to something and then solve for dx. Now, if everything works out perfectly, there should be no more x, as the sign x cancel out. This negative sign is a constant, or negative 1 if you will. We can take an outside of the integral at the bottom, but the negative 1 multiplied by negative 1 is the same as divided by negative 1. It's still negative. So that's why I just write the negative in front. Right? And then what's left of the problem is just u cubed and then du. The integral of that is u to the 4th over 4 plus c, or like negative divided by 4 is multiplied by 1/4, u to the 4th plus c, and then u is cosine of x, so we have negative 1 over 4th cosine of x to the 4th plus c, or we can write the 4th here, negative 1/4 cosine 4 of x plus c. So that's what we have. Right? So for let u equal to something. So for dx, substitute into problem, and then if it works out perfectly, we just have everything in terms of u, integrate that, and then write the answer in terms of x. Right, keep going. Now, on here, u should be x plus 1, right? Alright, so let's start with that. So derivative is equal to 1. Multiply the dx over, we have du equal to dx. And actually we solve for dx already because du equal to dx or dx equal to du, right? Multiplying across. Now let's just substitute into our problem. X will be just x. At the bottom we have square root of x plus 1. Square root of x plus 1 is u. And then dx is equal to du, right? Right. And we say, yeah, that's what we have. But usually if it works out perfectly, we should not have any x left. Here we have the x left that does not cancel to anything. So is that wrong, or we have to do something else? Well, actually it's not wrong. The problem here is if we have we want to write everything in terms of u because that's the goal here, but it's not that bad. If u equal to x plus 1, then suddenly we can solve for x, subtract 1 on both sides, u minus 1 is equal to x, right? Yeah. So even though we don't cancel the x, but we can rewrite that in terms of u. So this x will be written as u minus 1. Now we have everything in terms of u. That x is equal to u minus 1. Yeah. So sometimes if we don't cancel out everything, at least we can write everything in terms of u, and we still can integrate that. Still can integrate. Right. For this one, I will write this as u to the 1/2 because we're going to use the power rule, right? Right. We can split this integral. We have u over u to the 1/2 minus 1 over u to the 1/2 du. Right, and then use the power rule for, simplify them first. We're going to use the power rule, so we have to write everything as a power. By default, this is to the first power. Divide two things of the same base, and we subtract the exponents. 1 minus 1/2 is 1/2. Right, subtract the exponents. Now, this one at the bottom, move to the top, cross the line, change the sign, move to the top, it becomes negative 1/2. Right, now we have the power, and then we can integrate using power rule. Increase the power by 1. 1/2 plus 1 is 3/2. Divide by the same thing as the power, same thing as exponent. And then increase the power by 1. Negative 1/2 plus 1 is 1/2. Divide by the same thing as the power, as the exponent, plus c. Right. Divide fraction is multiply reciprocal. So we're going to have 2/3 u to the 3/2 minus, divide by 1/2. Reciprocal of 1/2 is 2 over 1, or just 2. U to the 1/2 plus c. Right, to flip, and then flip the 3/2 become 2/3, flip the 1/2 become a 2. And then finally, we just need to substitute u in terms of x plus 1. So we do that, and we have 2/3 x plus 1 to the 3/2 minus 2 x plus 1 to the 1/2 plus c. Yeah, so in general, if we don't cancel out, on the x, try to write the answer in terms of u. If we can do that, we can integrate, and we just have the integral of u, and that should be simple. At the end, just write the answer in terms of x. So that is indefinite integral, where we don't have the limit. What happens if we have the limit? Well, if we have the limit, I recommend that we just go ahead and change the limits. Right, so let's look at an example here. So we still the same thing, but since we write in terms of u, I recommend that we will change the limit in terms of u. So be mindful with that. So before I do anything, if I see the integral that from where the dx on the top, I try to move that to the back. Yeah, move the dx to the back, and then we can do the substitution. So this day you know that it's going to be u equal to x plus 3, right? Yeah. And then we can solve for dx. Take the derivative. Derivative of x plus 3 is 1. Move the dx over, du is equal to dx. Right, now in this problem, we also need to change the limit. U is equal to x plus 3 we have x equal to 0 and x equal to 2. when x equal to 2, u is equal to 2 plus 3, so it's 5. And when x equal to 0, u is equal to 0 plus 3, so it's 3. So 3 to 5. Right, now it's ready to substitute in the problem. One over x plus 3 cube. X plus 3 is going to be u. The cube still there. Dx is the same as du. Now the limit, instead of go from 0 to 2, it's going to go from 3 to 5. If we want to be precise, we can say originally we go from x equal to 0 to x equal to 2. Now we go from u equal to 3 to u equal to 5, because the integral now will be in terms of u. Right? So in that case, we can just say, if you want to be clear, we can just say u equal to 3, u equal to 5. And then integrate this, we move u up, that becomes -3 du. Right. Power rule. Increase the power by 1, -3 plus 1 is -2, divide by the same thing. And we do not do the plus constant, right? We let the constant equal to 0. This is in the section 5.3 fundamental theorem calculus. We just integrate, let the constant equal to 0, so we don't need C here. We will evaluate this from u equal to 3 to u equal to 5. Right. We do not need to go back in terms of x because we have the limit in terms of u already. We're just going to substitute in the numbers. I recommend it to do it this way. So let's just say instead of that, I will write as -1/2, right? Divide by -2 at the bottom, flip, it becomes -1/2, and then u to the -2. Once again, evaluate from 3 to 5. If it is clear, we can just say from 3 to 5 without writing u equal 2 and u equal 2. Right. So u to -2 I will bring down to the bottom. It becomes -1, u at the bottom, u square. Going for u equal to 3, u equal to 5. Now it's easy now. You can just put 5 in, put 3 in, and subtract them. So we have -1 over 2. U is 5, so 5 square. Subtract -1, 2 times 3 square. So we have -1, 5 square, 25 times 2 is 50, minus -1 over 3 square is 9 times 2 is 18. So that's what we have. -1 over 50, subtract -1 over 18. And that's what we have, which is 8 over 225. 8 over 225. Right. Now, let's check. When we have definite integral, when we have the limit, we can use the calculator to estimate the answer. It is an estimate. And you see this is the same as that. So can we convert this to fraction? No. See, so that is the difference between the calculator answer and our answer. This is the estimate of the calculator. And this is our answer. So the calculator only estimate the answer. They estimate the integral. They will not give the accurate answer. So that's why for this kind of problem we have to do it by hand. We have to do it by hand to get this answer. And then we can see it should be extremely close to the approximation that the calculator has. But yeah, if we want the exact answer, we have to do that by hand. And I mentioned this previously. If your calculator can give you the exact answer like this, that means you cannot use it on the test. Yeah, I will write on the final exam the rule that what you can use and what you cannot use. Right. Now we have that problem. So cube root of 2x minus 2. So look like u is going to be equal to 2x minus 2. And then we take the derivative. Derivative of this is 2. Move the 2 over du is equal to 2 times dx. Divide by 2. And we have that. It's almost like a routine. Now, u equal to something, take derivative and solve for dx. This one we have the limit, so we have to rewrite the limit as well. X equal to 0 to 5 and u is equal to 2x minus 2. So when x equal to 5, 2 times 5 minus 2 is 8. 0 times 2 is 0, so that's just minus 2. So instead of go from 0 to 5, it goes from -2 to 8. So we have the integral. The cube root 2x minus 2 is u, and dx is du over 2. Now, originally we have x go from 0 to 5. Now we have u go from -2 to 8. Right. Now it's good. We have everything in terms of u. That 2 here is a constant. I can take it outside and keep it at the bottom. Yeah, just need to put 1 on the top. So we have a fraction. Here we have u equal to -2 to 8. Yeah, when you get used to it, we can just say from -2 to 8 without writing u equal to. Cube root of u du. So it's 1/2. Yeah, now I just say from -2 to 8 because u is the only variable here. And we write this as u to the 1/3. And then use a power rule for that. The power rule for u to the 1/3, increase the power by 1. 1/3 plus 1 is 4/3. Divide by the same thing as the exponent, fourth third. Now this is the definite integral. So instead of plus c, we will have the limit -2 to 8. U equal to -2 to u equal to 8. Now, divide by fourth third is multiply the reciprocal. So that gives us 3/8 u to the fourth third from -2 to 8. Right? Then we can have 3/8 8 to the fourth third minus 3/8 -2 to the fourth third. Right. What is 8 to the fourth third? Should be 16. Yeah. Of course. 8 to the fourth third. 8 is 2 cubed to the fourth third. Multiply the exponent. 3 times 4 thirds. 3 and 3 cancel out. That's 2 to the fourth. So 16. So that cancel out. And so we have 3/8 times 16. Well, this we cannot do anything here. What is -2 to the fourth third? Too bad, that's all we have. It's going to be positive, right? Which is the same as 2 to the fourth third. So, it's not going to be anything nice and even, but we know for sure -2 to the fourth third. It's just the same as 2 to the fourth third, because the -4, so we write this, -2 to the fourth third will be -2 to the fourth, and then cube root of 3. So the top number gives us the power, the bottom number gives us the index of radical. So in this case we can just say cube root of 16 if we want to. Yeah, we can just say cube root of 16 if we want to. Yeah, so here I just say 3/8. I will rewrite -2 to the fourth third as -2. The top number is the power, the bottom number is index of radical. So simplify this, 3/8 times 16. 16 and 8 cancel out. We have 2 times 3, which is 6, minus 3/8. And then that just cube root of 16. Yeah. So let's just see what's that. Approximately equal to 6 minus 3/8. And then times cube root of 16. Cube root is under math. Cube root. Or we can choose here, which we can type any root. Sorry, that's terrible. 6 minus 3/8 times. If we go here and we use this option instead, we will say that is cube root of 16. Right. Now let's estimate to see if this is the answer we have. Going from 0 to 5. That cube root of 2x minus 2 dx. Right, as you see, it is correct up to this point. The rest the calculator estimated So the answer of the calculator is not as good as our answer. Yeah. So, and that's why for this type problem, we should do that by hand to get the exact answer. What the calculator have, what the answer in the calculator. It's just an approximation. By the way, I just want to bring out this also. So here we have u is equal to -2 to 8. We don't need to write in terms of x. If you want to do it, you can rewrite this integral in terms of x, and we say this is over 3 over 8. U is 2x minus 2 to the 4th third. Now if we write the integral in terms of this case, make sure you need to evaluate in terms of x. Right. So if we keep everything in terms of u, we're just going to evaluate in terms of u. If we want to substitute back in terms of x, make sure we have to evaluate in terms of x. So that's why I write this very clear. Well, not on this one. Now, on this one, I write everything in. Those are the values for u. Just substitute it and evaluate. Do not need to go back in terms of x. If we need to go back in terms of x, have to evaluate option x equal to. Right. Now, we have this from cosine square. So how do we do cosine square? Well, it's not something that much we can do. Usually this more likely we see in calculus 2 problem. So I will not do this. It's just to get you, you know what, I think that's important. So we have an identity. I call the power reducing. It's going to be 1 plus cosine of 2a divided by 2. So that is power of reducing. Power reducing. Reducing the power to that. So in this problem, I will rewrite this instead of cosine square. I will use that. By the way, like I said, this is more like the calculus 2 problem. Now for this one, I certainly can split them, right? And then we split them, split the integral. Yeah, I can just write that 1/2 cosine 2 theta. But I just put the 2 theta at the bottom. I mean, put the 2 at the bottom. Doesn't hurt. Now the substitution. Substitute 2 theta. Let u equal to 2 theta. So in that case, derivative move the d theta over move the d theta over, we have that, and then divide by 2. So du over 2 equal to d theta. Now let's change the limit. I just put this here. Theta, and then u equal to 2 theta. we're going from 0 to pi over 2. And u is twice that, so we go from 0 to pi, right? Now we can go back to our problem. Now the first integral, we don't have to do anything. We can just integrate that. Integral of a constant is going to be that constant, right? Evaluate from 0 to pi over 2. That is theta equal to 0. Theta equal to pi over 2. Yeah, we don't have to do anything with that. Next, the next integral, I'm going to use substitution. Cosine of 2 theta, which is u, divided by 2 d theta is du over 2. Now theta, we do no longer have limit for theta, but we have u equal to 0 to u equal to pi. Now, I forgot about that. This first one, I just substitute in the limit. 1/2 times pi over 2 minus 1/2. Put in 0. Now plus. Yeah, everything in terms of u, but we have the constant here. 2 times 2 at the bottom, which is 4. And we take both of them outside. So that gives us 4 at the bottom. U equal to 0 to u equal to pi. And cosine of u du. Yeah, that gives us pi over 4. That is 0 plus 1 over 4. Integral of cosine is sine, going from 0 to pi. Of course, we want to put pi in and put 0 in. Sine of pi, subtract sine of 0. Now sine of pi is 0, sine of 0 is also 0, so we have this 0, this also 0. So the answer is pi over 4. Now let's check. If we use trig, make sure it's in radian. Okay. Math, option number 9, going from 0 to pi over 2. And we have cosine square, I have to type as cosine of x square. Yeah, like that. And is that pi divided by 4? Yes, it is, exactly. Right, but like I said, the calculator will not give you pi over 4. The calculator can only give you that decimal answer, which is not enough. So if we want to get the exact number, the exact answer, we have to do it by hand. So like I said, this is more like the Cal 2 problem, where we have to use the power reducing. By the way, if you see this, if we see the sine square, it will be 1 minus cosine 2a divided by 2. Right, so that is power reducing. That's what we have for this problem. Right, moving on. Now we have this integral from negative pi over 3 to pi over 3, x sine of x squared plus 1 dx. Now, just do the substitution, right? Now, as mentioned before, usually we let u equal to something in the parentheses, but of course that's just a guideline. What should work is whenever we let something equal to u, we take derivative. It has to somehow resembling what's left of the problem. By this I mean, if we let u equal to x squared plus 1 and we take derivative, it is 2x, right? So derivative is 2x. Now, it have to resembling what's left of the problem, which is x here, so that should cancel with this x. That means the substitution is right. Right. So whatever we let equal to u, the derivative of it should somehow resembling or should somehow cancel with the x of the problem. That's what we have. That's what a good substitution is. Unless, of course, we might have something like this, where we have to solve for x as well. But, right, yeah, those are the rare cases where we have to do that. But usually, what we let equal to u, the derivative of it should cancel with what's left of the problem. So, we have that derivative is equal to 2x. Move the dx over and then move the dx over and then divide by 2x. And so we have u and we have dx. Now this one, let's change the limit. X and then u is x squared plus 1. Okay. X is pi over 3. U is pi over 3 squared plus 1. And negative pi over 3, we have negative pi over 3 squared plus 1. Actually, this should be pi squared over 9 plus 1. And negative pi squared over 9 plus 1. Then you say, what, the limit are the same, the integral should be 0, right? Yes, that would be correct. Since the limit are the same, the integral should be 0. Right, but we won't be able to say that yet, because somehow the limit are the same, the function inside still have to be defined. X squared plus 1 is going to be u, and then dx is du over 2x. The limit now is going to be pi squared over 9 plus 1 pi squared over 9 plus 1. Right, the x cancel out, the 2 moves outside. So we will have the 2 at the bottom. Have to put 1 on the top, so we have a fraction. Limit go from u equal to pi squared over 9 plus 1. U equal to pi squared over 9 plus 1. Here we just have sin u du. Right. What we need to show that this is defined, right? This function is defined. Therefore, the same limit, so this equal to 0. So we don't have to do much, right? Because we have the same limit. The area under the curve, if we just have the curve, and if we just have the width is equal to 0, we go from some point to the same point. So we just have one line. The line has no area. So that's why, because we go from this number to the same number, so we just have one line. The line has no area, so that's why it's equal to 0. So that's perfectly correct there, right? So there is an advantage of we don't change the limit back in terms of x, because if we change this in terms of x, yeah, those numbers are not the same, so we won't be able to say this equal to 0 directly. Yeah, so that is an advantage of changing the limit to u, and then at the end just substitute in for u. Do not need to go back to x. So that's good. And talking about this problem, what we see from the previous section, 5.4, when we have the opposite limits, we can show that this function here is an odd function. Then that will be equal to 0. So let's see if it is the case. Let's graph x, sine of x squared plus 1. It's going to be difficult to, well, you see it is symmetric about this point, about the origin. Yeah, so in that case, this is an odd function, and therefore integral equal to 0. Actually, I just want to do that real quick. If we have f of x equal to x sine of x squared plus 1, so if I start with f of negative x, I have negative x sine, substitute negative x into x. We have negative x sine negative x squared is x squared plus 1, so x squared plus 1. Of course, this is exactly as the original function, but with the negative. So that's why f of x is odd. So this function is odd. If it is odd, the limits are opposite, the integral should be equal to 0. By the way, just make sure that the function is defined as well. If the function inside is undefined at some point between negative pi over 3 to pi over 3, we cannot say that. But it is defined throughout from negative pi over 3 to pi over 3. Because psi is defined everywhere, x is defined everywhere. So that's why this is defined everywhere. So if it is defined within the limits, and the limits are opposite, the function is odd, it's going to be equal to 0. Yeah. Right. Last problem. Evaluate this. You said, well, that is probably the easiest example, right? Yeah, so let's just do that quickly. Let u equal to 2x plus 1. And we take derivative. Is equal to 2. Move to dx over du equal to 2 times dx. Or du over 2 is dx. I did hundreds of problems like this, so that's why I get kind of routine. And right, now we change the limit. I go from 0 to 2. When x equal to 0, u is equal to 1. When x equal to 2, u equal to 5. So we go from, instead of go from 0 to 2 for x, we go from 1 to 5 for y. I mean for u, sorry. This integral equal to, there's a 2. Of course, we just multiply it out and integrate. That's not even the problem. And then you say, why does this example do too simple, right? I just multiply the 2 out and don't even need to use substitution. Well, just want to demonstrate something real quick. So 2 to x plus 1 is u. We could not do this with more complicated problem. dx is du over 2. Now the limit, instead of originally from x equal to 0 to x equal to 2, now we go from u equal to 1 to u equal to 5. Now the 2 cancel out. Or if you want to do that, perfectly fine. The 2 on the top, this 2 at the bottom, which cancel out. So that's just equal to u from 1 to 5 du. Integrals u squared over 2 from 1 to 5, and that is 5 squared divided by 2 minus 1 squared divided by 2. So 25 over 2 minus 1 over 2. So that is 25 over 2 is, common denominator is 2. So 24 over 2, which is 12. Yeah. Subtract the top, keep the common denominator. That's what we have, 12. Of course, that problem is too simple. But what I want to demonstrate is, even in terms of area, 2 times 2x plus 1, that is the function. The area from 0 to 2. So this area, let's just calculate. This is 2 by 2, so this area is 4. And this triangle is 1/2 base times height. 1/2 base times height from 2 to 10 is 8. So it's 8. So the total area is 8 plus 4 is 12. Right. So in terms of area, it is 12. Now if we do the chain of variable, the area should still be the same. Now different function, but from 1 to 5. Now this is a rectangle, 1 by 4, so this is 4, and the top here is again a triangle, 1/2 base is 4, the height is also 4, so that is 8. Again, the area is 12. So that certainly works. So both of them is the same, even though we change the limit, different function, but the area should be the same. And just one more thing. So here what we just see this is that we have du, it's going to be 2 times the dx. What does that mean? That means whatever the dx, the du will be twice that long. But the area is still the same. Area under the curve from both cases will be the same. We change the limit, change the function, but the area should be the same. So that pretty much the substitution rule. With this substitution rule, we can do a lot of integral. So when we go to chapter 7, we will do a lot more integral. But I want to start section 5.5 here. As always, thank you for watching, and see you in another video in Calculus 1.